because Lowy, who was working in Commons Stack and now it's working on Gitcoin, also wanted to see this recorded. And as you will see, it's quite interesting because this project is using conviction voting in behind of it, and it's also something that Gitcoin could be interested. So let's start with a quick demo on osmotic funding, and then we can go deeper into the protocol, how the things are working behind of the scenes. So this is a project that we have been working on, a hackathon that has lasted during the last 3-4 weeks, and we have came out with an idea that is similar to conviction voting, but instead of releasing all the funds when there is enough conviction, we are releasing the funds over time at a rate that is defined by the conviction that people have on a proposal. So one of the metaphors that we are using is it is like a plant that it is grabbing some water from the soil, and it is conducting it to each one of the leaves, and when the plant knows how much water to send to each leaf in order not to put it too much in one of the leaf, but also keep the parts hydrated, the parts that are more interesting for the plant. For example, if the plant is going to grow in some way to one place, maybe it needs more resources. So let's say that the plant, as a organic being, can decide how to use the resources, and this is why the logo and the images of osmotic funding is about sections of the plants, of the trunks of the trees. You can see here the vessels of a tree that conducts water from the soil to the leaves and the rest of the plant. This is why we have this imaginary, and the idea is that you have a sort of pool in which you have some funds. In the case of one hive, it will be honey. In the case of let's say Gitcoin, it will be, for example, 100,000 DAIs, and people could be staking GTC, but again, each DAO will have their own tokens to stake. If we were doing this for honey, it will be honey, and we will be deciding with honey where to send the honey, like in conviction voting. So then we have the different grants that you can look for in the search box, and some of them are already into the protocol, and some of them you can add them. The ones that are already in the protocol, they need a minimum amount of GTC in order to be activated. If not, they are not going to receive funds. So there is this progress bar where when you have enough GTCs, the grant is going to start receiving funds. For example, this is the case. There is a rate per month, and then the amount of funds that has already been raised. So this rate is defined by the amount of available funds and the amount of staked tokens, using a very similar formula to the one that we have in conviction voting for the threshold. Now we will go to this specific formula, but basically, if there is enough funds and there is enough stake, then you will the more funds there are and the more stake there are, the more you are going to have this rate. There is a rate that it's 1,600, right? That is going to be like the target rate, and it may be changing depending on the stake and the funds that there are available. But it's like this is what gardens should receive per month. And then we have the rate that it had before, because I just started with this. The garden had a rate of 0 DAIs per month, and now it's accruing this conviction. It is changing the rate from 0 to 1,600, and it will take some time. But when it already has this, at any point in time, if it changes, and let's imagine that it goes to 0 again, it will not go directly to 0. It will go decreasing over time until it reaches 0. So we use conviction in this project as a way of smooth the change in the rate of a project. And I think that in some sort, it is what a plant is doing. It's like it is making these vessels bigger or smaller depending on the needs of water and nutrients that it has for a certain region of the plant. It does not cut completely the provision of nutrients. It just gives less nutrients over time. That's more or less the idea. And because we have the rate, the amount that is being raised is there over how to say that, it's available at any point in time. And right now we have two versions of the contract, one that is very simple and straightforward, and another one that is working with Superfluid. So these are directly streamed into the accounts of the people. And for example, imagine that Gardens has also some kind of stream that sends to their participants the funds, so they will be receiving directly the funds in their accounts without having to claim them. But it is yet science fiction, let's say. For now, we are only it is a project hackathon, a hackathon project that it's only proof of concept. This part is like coded but not completely working and not connected with the front end. We will be working in this. So I don't know if you have some feedback or questions until now.
I have one. Oh, go ahead.
Go ahead.
So with the total funds at the top, if you scroll up a little bit, there's a fixed amount, I think that's there's 100,000 DAI. Is that 100,000 DAI in a reserve? Is that 100,000 DAI per period? So like, how does it top up? If it's being streamed out from there, is there a built-in sort of, I shouldn't say built-in yet. I mean, you could presumably always tap it up, but is there an assumption about how the total quantity available directly affects the rates of osmosis? Like, if for example I came in and added money, does that cause an increase in the differential and thus increase the rate of diffusion? Or is there some base rate at which per period is being allocated so that the diffusion functions don't change dramatically when more money is added?
It could be a combination of both. It could be a superfluid stream that is coming into the vault, but it is agnostic to what the osmotic funding is going to be. And the osmotic funding is just going to read the available funds, and if they are coming as they are being served, let's say, this is going to keep constant. If not, if it's like a grant that we are giving, and for example, in the case of One Hive, there are those funds there, and we have it depends on the inflows of the DAO, right?
Yeah,
In
that's actually kind of the point of the question, though. Like, would this nest cleanly? So, like, suppose that one of these was the both the input and the output, like an instance of this. Maybe it's like a swarm getting funding, but then a sub team within the swarm getting funding within it. Basically, I'm trying to reason about the algorithm setup is such that the flows sort of equilibrate naturally, like in your analogy to plants, where if the sort of upstream flow was bigger, then there would be more in the downstream spot, and so the diffusion kind of propagates relatively naturally. Like, and again, I think the answer is yes from what you're saying, at least in the superfluid integrated version. But I'm like sanity checking this because I think one of the most powerful value propositions of what you've put together is the fact that it can function as intended while actually being totally modularized. Like a whole web of these, capillaries could emerge. I guess I don't know what the official term, the plant term for this is, but like this process could grow in a way that the inputs and outputs, both following the osmotic funding protocol, would make things actually flow through, and it would allow like new vessels to grow. With the Gitcoin example, it would be like if you are funding a working group from the Gitcoin DAO, and then within the working group you had substreams, which is actually something we have in the fraud detection group. Actually has subgroups even within it. You could imagine like very naturally nesting these things, and so I'm kind of prodding at that because I think if you design it and implement it in that direction, you could get some pretty incredible sort of like organic economic web growing up.
Actually, the organic thing, we could not talk so much, Michael, but some of the work that you have been doing previously with, especially with commission voting, which is the basis on the work here, it is also always trying to catch what the nature is doing. So we also try to continue with this way to do things. I will take a look on how we can be working on that. Of course, we are super. Um, we will be listening your feedback.
Yeah, we can talk about it offline too sometime. I'm super excited because I think it fits very much with a really good approach to dealing with what I would call sort of operational sustenance work, which is actually a big weak point in DAOs. I think it's really easy to fund and support like production. It's very difficult to do ongoing operations and maintenance, and this kind of thing puts them on the same plane. Like you can fund a team that does community management, you could fund a team that does things that are valuable, but maybe not quite as focused on shipping specific deliverables, artifacts. And because that's so difficult, it doesn't always get done. This would make it not difficult. It would make it very natural. And so, but then seeing those things grow and evolve over time according to these more biologic principles is super awesome. So I'm going to stop talking about this now. If you want to chat about composability sometime with a smaller group, maybe we can look at the equations and see whether the implementations and the equations together kind of create that, like replicate that organic growth dynamic that I think this really does make possible.
Actually, I also would like to present Didi here from Superfluid. He has also been looking for how to combine these different flows just in one. Maybe you can present yourself, Didi.
Yeah, hi guys. You hear me? Yes? Okay. Yeah, I'm not sure what I can tell you. So I joined Superfluid a while ago, and I have been thinking about streaming on Ethereum for many years now, and was pretty happy to find Superfluid because they even went further and generalized the idea of real-time agreements. And what you are looking into is one of the examples where I think this gets very interesting, because already back then, when I built a first prototype for a stream with constant flow rate, I started thinking, okay, actually it doesn't need to be like that. The flow rate could be a function itself, as long as it's monotonically increasing. And I think it's very cool that you seem to have a use case where this actually makes sense, and I'm really interested in figuring out together with you what such an agreement should look like. And I mean, you already prototyped an agreement, so I will try to, yeah, we should get that done. We need to figure out what exactly it should look like and how generic it can be, because I think it cannot accept just any function, but maybe it should not be too specific, so that we don't need an new agreement type for every type of function. But let's find out. And by the way, I love this graphic you have for this project. Can't stop looking at it.
It is fantastic. It is well. Thank you so much for having come, and it is fantastic to have you here. You still see my screen, right? Because my computer sometimes does some weird things. Okay. So I would like to, in some way, explain how it is done. And I came with 3 examples that can build one on the top of the other. In order to start, I will present a changing flow that is changing from one moment of time to another. So imagine that in 30 days, you pass from getting 10 tokens per second to 40 tokens per second. So this is, and after that, your target rate is always the same. It's your rate is always the same. So in order to define this, let's hide this. You need an initial rate, a final rate, and a time, right? We have done something similar with the osmotic funding, but following the equations of conviction voting, but we think that we could make it more simple than that. And let's start with this one. Initial rate, target rate, and time. So if you move the time, you move the axis horizontally. If you change the target rate, you are moving the higher part, and if you change the lower rate, you are moving the lower part. So now that we have this, how do we know how much funds we have get at the 10th day? Because if we were having a rate of 10, it will be easy. It will be 10 multiplied by 10, right? It's this square here. But we also have been receiving this part of the triangle here. So actually it's very easy to calculate. We just have to sum this square area here plus half of the square area here. And we can do this up to the time that we have finished. So we can sum this part here plus the area of the triangle. And after this moment, we can just sum up the area of this rectangle until the point that we want. So for example, 60 days, it will be this area plus this area plus this area. And in order to have that, it's as easy as doing these calculations. This line represents the average rate from the 0 point in time. So multiplying, for example, for 40, we have this 28 over here. 28 multiplied by 40, it will be the token that we have received over until now. It will have this area that is behind this. It's like doing the integral of this function. You are just doing the integral and dividing it by the x-axis. That's it. This is the integral of this function, and you are dividing it by the time that you have been waiting, so you obtain the average rate. This should be one of the... It is very easy to understand, and it should be the first agreement that we implement with Superfluid in order to do something that is useful and can be tested, and it's like the first step, right? Because right now the thing that we have is only a normal, like, flat rate that if you change, you have to recalculate. You have to do a snapshot, and from that point onwards, everything is new, and you don't have this differentiate growing or slowing down. Sorry, it will be.
So I want to add something actually. So you're doing quadrature, so numerical integration. So I sent you I sent you a link. It's a simple demo, but I can also probably send you another more robust reference. But most importantly, there's actually a lot of literature on numerical integration, which will mean it'll define to the questions from Didi about what is like what you can generalize is basically going to come to what you're going to how general your numerical integration is going to affect how general of a function you can deal with. So as long as you're doing polynomials like what you're doing here, you get exact numerical integration using like a trapezoid rule. It's a way of solving for the shape of the square plus the triangle. In general, there are numerical, it's called quadrature, sometimes numerical integration. If you do a little bit of reading up on numerical methods and in digital signal processing type applications, you can find basically the families of numerical integrations that are more or less exact, and the circumstances under which they fit with different analytic functions. And so literally your choices about what kinds of functions to support basically depend on how much complexity you do or don't want to deal with in terms of numerical integration. And also there are trade-offs in computation, like the methods. You can get more and more computationally intense methods that integrate more and more sophisticated algorithm or like equations, but then of course more gas, etc. So there's like a nice family of well-defined problems in quadrature from the existing like engineering literature to help you deal with this family of problems.
This link you mentioned, where can I find it?
I sent it to you in Telegram. It's a public link from CADCAD where I had just made a demo of sort of event-based quadrature because it was like I don't know, it was maybe a year ago, because I was explaining this to somebody else at one point. The main difference between this demo and the regular trapezoid rule is that in most engineering applications you have fixed intervals, but in time, blockchain networks have time varying intervals that you're actually doing computation at. They're not discrete time chunks of exactly the same length and time because of the way blocks work. But so this particular demo is one that I've written and then one of my teammates cleaned up for numerical quadrature with variable time periods between computations. But then the more general literature has quite a bit on numerical quadrature, this idea of integrating functions in discrete computation. And I don't want to derail you too much, but given that was the main question that came up about like what functions can we support and how general, that's basically going to be, how accurate is the integration? and how much computation you're willing to expend, with the caveat that some functions, like the one you showed, have exact integrations via what you effectively did was a trapezoid rule.
I shared it in the Luna Swarm channel, and I can send it to you as well, Didi.
Thank you. Yeah, that could be very helpful.
Okay. And the most important thing of this, I think, is that there might be different flows that comes and flows that goes out, and the constant flow agreement is very easy because you are just summing and you are just adding and subtracting the amounts, and it is very straightforward. You can store what is going on, and you don't have to loop over all the flows and know how much you have. It's like, in order to know which is your balance, with the constant flow agreement, it is very easy. With this kind of things that you have to integrate, you have to go over and over if you don't discover, if you don't know the way to sum different flows that may have different times, or even if they have the same time, you have to sum them up. So
I've got a question. I just want to make sure I have a high level understanding of the two lines. So in the chart, is the red line the conviction of people supporting that stream, and the blue line is the actual stream that they get?
Not yet. We are not yet there. We are not yet with the conviction. I mean, we are not yet with the support that people is giving. We are only talking about a project that is sorry. We are only talking about rate changes. So if a project starts with 10 and then people decide that in the future it should receive less, like in that case 3, how it will be decaying over time. And this is the part that we are using Superfluid. Then, in order to decide how much should the project receive, the rate, we can use another formula that, in the case of conviction voting, is called the threshold formula, but we have changed it a little bit in order to give a rate instead of a threshold. So I can go into it, but I just want to say that in order to work together, it must be we have to sum all the flows that are coming and going out and receive a net flow that should have I don't know if it's going to have the same shape, or depending on the time that you started, it may have different spots, different points that have this change in the rate.
Yeah. So with regards to the conviction voting usage, then this is actually the version of conviction voting that I remember I think you and I talked about it a long time ago, where you're picking a parameter rather than just generating a discrete event. The original paper has some reference to this, where you're using it as a form of dynamic average consensus to select dynamically a variable parameter, and that parameter is a parameter of another system, in this case the payment rate. So the conviction votes are actually being used as a kind of signaling of preference, and that signaling of preference is generating the rate parameter, and the rate parameter is determining how much people get paid.
The way that it is done right now, you define which is going to be every time that somebody is staking or unstaking, they change this
rate parameter. Well, effectively the rate, which
The-
I'm
the-
calling rate
the,
parameter because I'm
the,
thinking of it.
the target rate, we call it.
Yeah. Right.
So,
So go ahead. Sorry.
so the idea is that when we have this changed, then the line is drawn differently and goes to that part over time. That's the idea.
Right. So it's essentially a multiple order controller. You have a plant or like a mechanism that determines the payout, and that payout thing has a rate, which is what you're calling the target rate. So there's like there's the rate that you're actually being paid at. There's the target rate. So this ends up becoming a double integrator because the first integrator is the one that you're showing me now, the one that allows you to charge up the rate to the target rate from the current rate. But then the target rate is controlled by basically people participating in the conviction voting signaling, which is itself an integrator. So you actually have a double integrator, which is actually in a lot of ways really good because you don't want funding levels to change too rapidly because that makes it really difficult for people to plan and budget and actually do their work or whatever it is that's being supported if these values can change too fast. So it's actually kind of cool. I'm curious to see some some simulation of the effects of the double integrator as opposed to a single integrator. But I do in principle like the idea of having a control, like a payout mechanism with a target rate, but whose target rate is set by the conviction voting, which serves the function of there's like a social integrator, and then there's a plant level integrator.
Mm-hmm. The good way, I have here the thing that we have implemented in the hackathon, and we could discuss if the exponential decay that we are using as a formula could be replaced by a quadratic formula, which would make the integration way easier without logarithms and these things. Also, it is implementable with Solidity. We could get it. It may have some errors on rounding errors, but it is something that is there.
Yeah, I don't think you need the log versions. I mean, there's enough different variations of diffusion processes that you can use diffusion processes that are not like, I don't see a reason why you need to use a log-based diffusion property for this to work. I think you do have some tuning there. The shapes of those curves as you mess with. Are you able to mess with the curvature? Because I bet you if you look carefully, well, I know that you can make polynomial approximations of log functions. So there's versions of these that if you made a large enough polynomial expansion, you could eventually recover this. Again, trade-offs between the computational cost and the precision, but I'm not sure that you need the precision because you just need the shape. It's not as important to get the exact function the same. It's just like shape and relative sensitivity that'll affect whether or not it works.
Okay, I am going to introduce first what we have here, just for not lose anyone, and then we can go back into this discussion. So let's introduce one thing after the other. So this formula here, it is defining which is going to be the target rate over time. So it is going to be like, okay, depending on the amount of stake that we have, and depending, stake is this S here. So if you have a very small stake, the target rate is going to be 0. You need at least a minimum stake in order to start growing the rate. I don't know if it is seen properly. Maybe I should just. So from the first part, whatever you stake, it is not going to increase it, but from there, it is going to be increasing until a point. There is a maximum point of if a grant is already receiving 10,000 10,000 dice, it's not going to receive more, and this is defined with this B here. This B is the amount of funds that a proposal can receive, and we also have this T parameter which defines which is going to be this minimum stake. Okay, so if the minimum stake is way less, then it is going to be way more because we don't have this high requirement. So these are the parameters, and now we can start adding the rest of the things. So we have now which is going to be the target rate with these parameters here. Let's make it 5,000 DAIs per month for example, LunaSwap, let's say. So now we have this formula, which is very funny because the target is 5,000, and the thing that it's already receiving is 5,000. So it's not going to change, right? It's going to be constant. But what happens if instead of starting from 5,000, we start from way less? For example, from here. It's going to grow over time, and the same will happen if we had whatever. Let's start from 2,000. It will grow up until here. We are using a formula that is an exponential decay. So we have this decay here. I still don't know how it's called. It can be derived from the half-life of the... If you look for exponential decay in Wikipedia, there is a lot of information on how this is working. I think that this is not so easy to configure for a developer. It is not as easy as define which time you want to receive the target rate. This is why I am inclined to use another formula other than that, because you also can have these shapes with a quadratic formula, and it is way easier to integrate. But just for a good understanding, this formula, what it makes is that over time it reaches into the target rate. Well, it approximates into the target rate, and in order to know which is going to be the area below the curve, we have to integrate it, and doing the same thing that we have done previously, we can define as well which is the average rate. So for example, at 5,000, at 6,000 seconds, I will have this amount per second, let's say, and you can multiply it by 6,000, and then you receive you know how much amount of tokens you have. I don't know if I am very clear. English is not my native. But what we are doing is to integrate it in order to know every second how much a person is receiving. And this is the integration is treating this first formula as a constant. So we are just treating them differently. So this is what you were commenting, Michael, about having two things that are interacting with each other, but one does not depend on the other, which was essential for doing the integral. If not, it was very difficult.
I think the main thing that I was poking at was the difference. There's a sort of concept in modularity of this where you have the algorithm where you compute the target rate, and then you have the algorithm that uses the target rate and the current rate to compute the realized rate, or the rate that happens during that period, and then
Yeah.
the realized rate is what you're actually paid out against. But then you have another algorithm that operates a layer above that updates the actual target rate. So you end up having to do, in one time step, you have to basically, in one computation, you have to do update the target rate, then update or realize the rate, and then like account for the flows of the realized rate. And so the numerical integration is basically, as I understand here, then you're doing a numerical integration when you realize the rate. You determine how much everyone got paid during the period that passed between that change and the previous change, which is the part of the reason I sent you the demo I did, was because it contained the variation of the more standard trapezoid rule, but where the time periods between the events is changing. And actually, there should be some Solidity implementations of stuff in that family in the Rai code. I'm not sure how much of it's open source, but some of the CAD models for Rai have been open sourced. So they're floating around. For people who are familiar with that, that's the reflex index, the sort of stable coin based on some control theory concepts. So we're digging at a lot of the same core mathematical, like computational, sort of integral and derivative type signal processing stuff. So it's really incredibly cool to see it manifest in this design. I think it's a really, really fruitful territory that's going to get more and more attention. So the POCing and dogfooding here is really the only way to make like what I would consider best practices and dynamic, real-time, decentralized resource allocations viable in real life and not just in academic papers. And I can make fun of that because I wrote academic papers about that.
Okay. The challenges are maybe start with this, which is going to be easier, because also the challenge is to implement it with Superfluid. And then there are other things that are going to be challenging. For example, if this is not clearly defined, the amount of funds is not clearly defined, and it varies over time, then you can have a grant that is overpaid, let's say. And when you update your stake, even if you want to add more stake, what you are actually doing is to update the rate in a way that it's going down. So there are some parts that are not going to coordinate well in the current stance.
Yeah, one of the techniques for analyzing these kinds of algorithms that you can do over the math, not just over the implementation, is to do what is effectively partial derivatives relative to the variables that are changeable by the actors. So a lot of the times you're going to want to be able to say when, so an invariance occurs when there's a mechanism that mutates a variable, but that an input variable, say, or a parameter, but then the effect, the thing you care about, say the amount you're getting paid per period, is unchanged by that mutation. But there are also like positive and negative relations where you take an action, like the example you just gave, where maybe you stake more. There's going to be circumstances under which taking that example has the opposite of the intended effect directionally, and that's basically can be thought of as the region in the state space where the partial derivative with respect to the stake causes a negative effect on the payments as opposed to a positive effect, which is what is normally expected. But analytically, you should be able to determine which regions of the sort of state of this thing actually have that property. Not that you necessarily need to do a ton of analytic work, but in my experience, for the kinds of algorithms you're talking about right now, it can be really tricky to make choices about functional forms, and there are often like sweet spots, certain functional forms that have really nice properties with respect to their partial derivatives relative to specifically the things people are allowed to change. And so your requirements, almost UX requirements, come down to picking functions such that, well, they just behave intuitively. Like the direction of the derivative in the partial derivative of the mechanism exposed to the user is the direction they expect it to be. And if you have a functional form that violates those expectations and certain circumstances, then maybe that's less good than one that doesn't.
So instead of, which is your recommendation with the formula? Should we get rid of the exponential decay and go for formula that is, for example, this quadratic formula, which
So I guess maybe for people's context, this meeting came about because we were going to meet and talk anyway, and we decided to make it a group call. So I apologize for if I'm like dominating the discussion. If people have other comments, feel free to jump in. But I'm going to answer his question now. I'd still probably lean towards something with an exponential decay for its for its non-thrashiness. So interestingly enough, if there's no one touching this thing, the quadratic looks great. Like it feels nice in a very simplified example. But if you've got lots of people interacting with the same system, this is actually going to be jerkier than the exponential one. The exponential one is a smoothing function, so it's sort of and it doesn't have to be the ln alpha. It can be the alpha to the x one, the green line, not the blue line. The blue line that you had was going to be almost impossible to implement. The green line version.
Which one?
No, the screen you're on, not the red and blue, the green and blue we were just looking at. This one. So you showed those two functions. I was just pointing out that the function in blue with the natural logs in it is like going to be basically a royal pain to deal with, whereas the one that you have in green with just the powers, like you want polynomial approximations of logs and exponentials, not the actual natural log. I don't even know if you can implement ln of something.
We have it. We have it implemented with a library that is available.
Okay.
It is giving some rounding errors, but it's
Okay, you need fixed point, like decent fixed point libraries, and I don't know that there are much in the way of fixed point libraries in Solidity.
It is using a precision of 2/64, and it is. We could not make a very good approximation. There are some tokens that are lost.
Yeah, it's fine. I mean, I'm like poking at it a little bit because there are ways to get computationally efficient approximations of log, but it usually depends on if you know where you are. So like if you're close to 0 or close to 1 in particular, not close to 0, but close to 1, so that you can represent the thing such that it's like ln of 1 plus epsilon or 1 plus or minus a small value, then you can, there's different approximations of log that are way more accurate. But that's sort of neither here nor there. I think what I'm kind of getting at here is to your question about the simplified sort of polynomial expression with where you just do a straight line and you interpolate. That version is going to have this property where I feel like it's a little more jerky when people change things because the slope isn't going to change smoothly. The slope is going to change in little chunks. So like if I come in and change it, the event happens, and if the value is kind of going up and down a little bit because different people are interacting with it, I don't think it will suppress as much of the high frequency noise as more of a smoothing function would. But that's based just on like intuition and experience. It may not be enough to matter. It's possible that the the gains in the computational efficiency will offset the the perceived kind of effect of not attenuating the noise. But that's normally something I would test in like a simulated environment, like poke at the couple different formulas so you don't have to worry about them in Solidity just yet, because it's really still the property of the mathematical object. But then there's the question of the property of the implementation. So if you have a better mathematical object, but it's still a lot harder to implement, you probably prefer the worse mathematical object because you can get a cheaper, higher fidelity implementation of it. So you're dealing with this sort of, unfortunately, the perpetual engineering trade-off space of the design and the implementation and teasing out what actually meets your use case. So my intuition, I like smooth functions, but if the difficulty of implementing it is high enough, it's still probably better to go with the first one. So basically what I'm trying to say is the two that you've shown me, they both have pros and cons. Depending on your priorities, you might pick one over the other. I like smooth things, but I also am used to working in environments that don't have quite as much difficulty with numerical approximation. So the Solidity language is not really very mature in terms of how it handles analytic functions. There's not really there's no existing libraries for things like quadrature, what I was talking about earlier. There's not a lot of tooling for making efficient the computations of things like log, or making efficient dealing with basically these kinds of equations in general. This is, often you learn this in like embedded systems, like when you're learning to program low level, like hardware systems that have very little computation, they need to spend very little power, but it's like people who work on physical devices who learn to do that kind of low level programming, and the kinds of language optimizations that have been created to ensure that numerically sophisticated algorithms can get implemented on really low power, sort of low computational power, low power consuming, low memory devices. And they have a lot in common with smart contracts and blockchains because of that. But the particular expertise really hasn't propagated into Solidity. So things that I would normally think are okay might still be an overreach for trying to get them implemented. And so with that in mind, I'll say I'm biased towards the one with the smoothing, but that's because I would be, at least from my historical training, comfortable using tools that could handle it even in a computationally constrained environment. Given that doesn't seem like Solidity is very mature in that direction, you might just end up sticking with the polynomial.
This one, a sec, because we have the polynomial that is also smooth.
Right. The smooth polynomial is my favorite of the ones that you've shown me, given what I just said about Solidity.
May I briefly ask something here? Am I right assuming that we can add polynomials such that we would have such an agreement type that we could always aggregate them into one, as we are doing with constant now? That would work, right?
We still don't know. Probably this one is going to be the easiest. And Michael, I didn't understand if you don't like any of the two that are smooth, or you think that this is better.
Of the three you showed me, let me look and see if I can get their names right. So if you click on osmotic funding, the third one over. So the equations that you have in the row with the green line thing, to me, that's the kind of function that I would expect to be working with. And so then if you go back to the adaptive flow quadratic one, I feel like this drawing that you have works, but I would generally bias towards things that are constructed more like the thing that was in the row we just looked at. But I realize I'm just kind of like poking around at this. From what I can tell so far, what you're doing works fine. I would test it and look at whether it actually meets the expectations of your users, mostly in terms of the direction that things change when you mutate them. So like this sort of partial derivative like testing, like mutating individual points and seeing if the net change on the output variable is what you expected. So kind of input-output testing. But like it's really difficult to do more than just kind of pontificate while looking at the screens and not having like a whiteboard session, because normally I would be like doing derivations to try to feel out what I like. From a shape and drawing perspective, I'm just going based on like intuition. You know what I mean?
Yeah. Okay. But I still don't get a good recommendation. For
The
sure,
one,
we
the
will
one that
start.
you're showing now is I wouldn't. Okay, this first
Sorry.
one. God damn it. Okay, so click to the left. One more tab. I probably wouldn't use this one because the edge in it it's just sharp. You've got the next one over, which is a smooth version of this. I think that's better. I would prefer this to the one before it. Is that helpful?
Okay, of course.
Cool.
We will start with the first one in order for simplifications, but then we will go with this one.
Cool. And I wasn't trying to be overly prescriptive. I was just like kind of feeling my way through what you're showing me, and I would say as a
Excuse me?
there,
No. I don't. I think that somebody else said something. Go ahead, please.
yeah. So I was just gonna say, I think the things that matter is the composability more than anything else, and the intuition about the direction of the partial derivatives. And some of those things you can test just by running tests on your software, like just once you get it up and running, doing these mutations over the inputs and seeing how it affects the outputs. And that if that makes sense, then it'll be fine. So then after the directionness, it's really just how noisy it is when things happen. So how big are the changes relative to the other changes? Because if it's a system that many people are interacting with, you want it to smooth the noise, not preserve or magnify it. So once you get past basically directional correctness, mutations, people can do stuff, they do things, the outcomes that happen are what they expect in direction. Then when you assume many people are interacting with the same system kind of concurrently, that generally implies some degree of high frequency noise just because people are changing. Then you want the system effectively to attenuate the noise, at least insofar as it's canceling out. Like I'm going to add some conviction, you're going to remove some, then the net effect that the person who is getting the funds experiences should be very little, if any, because the those activities canceled out and they were higher frequency than the slower frequency funding stream. But if in general we had lots of people sort of adding conviction, you'd see that's like all in one direction, then of course we could see there'll be a lag in the effect, but then the person will experience that change in a way that would have been rejected if it was just the same amount of activity back and forth. And so there's this sort of like sensitivity to the composition of the activity, which is like, so it's direction, magnitude, and basically this kind of noise sensitivity are the kinds of things that you want your, for lack of a better term, maths to accomplish, the signal processing that's going on by virtue of your choices of equations here. And then the composability is if these things work in such a way that the flow, the diffusion makes sense as a one's input is actually the output of another one, then I would say that's the point when you've really like hit all the boxes and made something really awesome that can create this kind of funding flow web. But yeah, I'll repeat it one more time. There's the directionality of the mutations, the magnitude sort of feeling appropriate, so like the sensitivities of those mutations, then the sort of noise rejection property, which you really should get almost for free since everything you showed me was at least an integral, if not a double integral. And then that last bit, which I think really plays to its broad power, is whether it continues to exhibit the properties when you stitch it together, when you connect one's input to another one's output, which can also be tricky. But I believe if you implement this correctly, it will be such that that happens naturally. Like it shouldn't lose its properties when you wire it together like that, because the filling of the input slot of one of them from the output of another should just kind of increase the concentration of funds on one side of the diffusion membrane, and thus like flow through. And it's not immediately clear how to get to that point, and if you'll need to do iterations on the design to achieve that. But as soon as you have working version of the individual piece, I would recommend doing this kind of integration testing and seeing how it behaves when you plug it together, and continuing to iterate on it until it's like networking capability meets your sort of expectations. And that would make for a pretty incredible, very plant-like value flow system.
Okay. I will have to rewatch this video. I hope that Metaverde do not lose the file, please, because there is a lot of information and we have to process it.
I hope so. I hope so. It works. We'll see. Go okay.
Okay.
And you can follow up with me if you need to. I know it's a little weird because I'm glad so many people came, because it's cool to have the community, but I'm also like, I was expecting it to be like us and 2 people just to be kind of a jam session.
I mean, it is a Luna Swarm, and it has been a lot of time that we did not do anything. So it is great that many people is just let's open to all the feedback and comments that people may have.
Can those Desmos pages be shared? Are they shareable?
The Desmos, if I can share them.
Thanks.
Okay, I can share them in the Luna Swarm as well. They are also in the Superfluid Protocol channel.
Oh, okay.
But it's also very good that they are here. Okay, if nobody wants to say anything, I just have an announcement to do. We have received the news that Superfluid has conceived one of the prizes to this project. So it's going to be highlighted in the blogs, and it's a ETH Global Sponsor Prize for the osmotic funding, and we are hoping that we can develop this project until a point in which it's usable for people to move the funds around. If somebody else would like to tell something, I see Paulo here and Gabi, who are other people from the team.
Oh, yeah, really glad to see this project going on, and I think once the superfluid integration is finalized with the latest changes that Paulo worked, it's gonna be super powerful to integrate in some other ways. So yeah, excited to see the next steps.
Hi everyone. Yeah, I'm also super excited to, once we have a clear specification, to start working on creating a new agreement for this, and continue working on the one that we did for the hackathon. And yeah, I hope that we can have a new funding system with these variable flows. That will be super interesting. Yeah.
Okay, I think that it's enough for today. Let's follow up with the. I'm still not sure where it's going to be the best place to follow up with osmotic funding. Maybe we create a new channel in OneHive, or we will see. But for sure, we will be keep working on this, following the three main things that we want to work now is have this agreement that is usable by Superfluid, that has the this change over time of the rate, and it works well with many flows that come and go out, so we can sum up all the flows in a constant time instead of having to loop over them. So maybe the first one that I showed to you, it's going to be the easiest one, but let's try to make the second one, which should not be that difficult if we have the first one.
So I have a question, since this is the Luna Swarm meeting. Like, if people are interested in like helping select, with what you're looking at now, what you did in Desmos is like the, a good starting point, but in reality, you are still like effectively doing this dynamical system signal processing thing. The fastest way, in my experience, to hone in on some algorithms choices would be to make something like a CAD dynamic model where you just go in and swap one piece. So you create scenarios like, hey, people show up and they add and remove conviction from a handful of, specific proposals, and then you would follow through the mathematics and iterate how much they make and kind of do all the accounting in each loop. And so then you'd run the thing and you'd see what happened, and then you would actually go in there and you change out the different equations that you're suggesting and look at how those different equations behave. But it's a lot faster to play with the mathematics in a easy to code environment. Now I say it this way because this is Luna Swarm, and if there are people here who wanted to, say, grab one of the existing CAD models and like tear it apart and put it back together with this idea, depending on how good your Python skills are, that could be done in even a few days. But in my work, the way that I would come to the decisions that you're asking about would be literally to just make a mock-up of the economics, right? And then start throwing in the different equations and saying like, okay, well, what happens if I use this equation? What happens if I get that equation? How different are the results anyway? And that helps me make trade-off decisions like, hey, I know that maybe this mathematical equation is more precise in one way, but if I can't implement it efficiently, then I might not want to use it. But then, like, how much do I gain or lose is actually going to be part of it. Like, am I willing to incur more computation to get something with more sophistication, or is the benefit of that sophistication all lost in the numerical approximation? Or like stuff like that relates to the mathematics and the signal processing properties, or even the composability properties of the algorithms are way easier to iterate on rapidly in like literally a modeling like clay environment. And since you've already basically built the stone structure that covers all the accounting, the idea would be, if you made an adaptation to the algorithms part, that should be sufficiently modularized in your smart contract code that like swapping out a new equation is not the same as rewriting the smart contract from scratch. So you end up taking the math design and the smart contract development, and you sort of, you can't completely decompose them, but you can set them as like parallel synergistic paths where the sort of modeling and math research is banging against the different equations and looking at the different circumstances under which they do what you want or don't, and the other is actually making sure that you have a robust, modular, high quality implementation. And then if you do come in with a math change, it should be really localized to like one method, right? Because you would have made an input output mapping that literally says the input to this is this data payload, and the output to this is set this variable. And so if you make sure that the math bit is really got a tight surface like that, it all keeps the same inputs, it keeps the same outputs, and the only thing you're changing is the equation itself, then you can actually let your colleagues who want to play with the mathematics do that and explore it using, again, we use CAD models in Python, but when I was doing robotics, we used MATLAB to do the math work, and then the implementations were in low-level C. Like they were mostly, on board, like C on microcontrollers. But like those two teams weren't separate from each other totally. They just kind of separated the problem from designing the mathematics and implementing the software. So you can have that, like I think that works in the setting you're working in. You'd be able to separate the person who did the mathy design, which would have been MATLAB in the robotics case, working in something like Python and CAD, and you can still have the people who are implementing the actual control logics in production working in Solidity, which is, in this case, the equivalent of what would have been C. And I'm old, so, I'm not saying people, that's just me talking about shit that I did 15, 20 years ago, so I can't say for sure that the people who are doing those tasks are still using C, but I wouldn't be surprised if they are.
The way that we would like to make it is having different superfluid agreements that uses different formulas, and then you will be able to choose. We are already doing the separation between the target rate and how the rate is reached over time. So this is already a separation.
So you should definitely look at the Rye code base. I don't know how much of it is public, the Solidity, but I feel like it probably is. I know some of the CAD modeling is public now, because the way that controller works is that it sets a target rate for it's a different kind of, it's a price in there. Rye is it's like a variation on the old Maker design. So it has a target rate for the price of Rye in order to actually work, and it's changing it according to, I think it's currently set up as a P controller. The analysis was done for PIs and actually possibly even PIDs, but you don't really want the derivative term in a crypto economic system. You'd want integrals, so it's PI in most of the analysis. But the point is that some of this pattern, the idea of a target rate, even if the target rate is a rate of a different dynamic process, is present in that code base and analysis. So if you're looking at learning about various interactions between signal processing and control theory concepts applied to crypto economic systems, that's a production system that has some of those concepts in it.
Okay, that's very good. I will for sure look at the code base.
I'm pretty sure the contracts are open sourced, all of them. Just a quick comment regarding agreements. I think if we can manage to build an agreement which supports a whole class of functions, let's say range of polynomials, that would be better than more agreements, because actually it also needs to iterate over agreements, so it's better if we have less of them.
Okay.
You probably just want some sort of family of like parametric family, so like one or two parameters that allow you to sort of tune the agreements without having everyone have exactly the same one, but as long as they share the same functional form, you wouldn't need different code bases.
Yeah, exactly.
Yeah, we have many restrictions from many places, so the simpler we did this, the better probably.
Yeah. Well,
okay.
That's the other main finding that I think you should look out for, is that like the solutions, you really do want simple solutions. You just want to hard fought simple solutions. You want to like fight through from simple to more complicated and then prune the complicated thing back towards simple while preserving the properties, because you end up doing this thing where the first simple answer probably has some properties that aren't great. You add complexity in order to resolve the problems, but then it's too complex. So what you do then is find out how to trim without losing the properties that you added the complexity to get. And that sort of negative design step is what a lot of people are missing, actually. And just doing loops of adding until you get the properties you want and removing while preserving them is a real trick to getting awesome simple solutions.
Totally.
Okay.
Cool. All right. Well, thanks. Thanks for having me. I'm glad we had a chance to catch up, Sam. I've been looking forward to chatting with you about this. So.
That's great. I also would like to share to talk with me to talk with you more. Let's keep working on these things, and especially we are quite excited with osmotic funding. Let's see where it gets.
Cool. Well, thanks for the presentation. I guess thanks everybody who came.
Thank you.
Okay, let's close it here then.
Thank you, everyone. Bye.
Thank you, everyone.